Okay, so if you go down, and we had kind of talked about this a little bit last time, but if you look at your formula for the sample variance, you will see that it is very similar to your population variance, but the difference is here, instead of dividing this by n, we're dividing by n minus 1, and of course the same thing will happen when you take your square root to get the standard deviation. So right underneath that, in this little paragraph, we're basically talking about, when you're going from a population to a sample, there can always be, remember we had talked about sampling errors in chapter 1. So to kind of avoid some of those sampling errors, because, if you take, and we'll use the example of, again, let's say we're just trying to compare maybe how male students perform versus female students perform in maybe, a class. And so we can take maybe the classes that I am teaching, and then maybe some of the classes that, maybe our English teacher is teaching, and just kind of compare, grade levels and that kind of thing. So what happens is if I take all of my classes and our English professor takes all of his classes, well, then that's our sample size, right? But then what happens if we went and got maybe some of the ag students in the ag classes, and then maybe we got some of our welding students? So that would be a different population then, right? So your results are always going to be slightly different depending on where you pick your sample from, and obviously sample size and all of that. So to kind of get that generalized idea of avoiding the sampling error, and with each sample the results can be a little bit different, to compensate for that, we actually divide by n minus 1. So you're kind of taking some of that difference into consideration. It's not always going to be the same as if you were able to take the entire population and do your study, as opposed to a sample size. But to avoid a little bit of that error, we divide by n minus 1. So of course, those note cards that I have you guys write down for your exams, just make sure you are writing the accurate information down, so that when you're looking at an example, you have to first decide, is this a population or sample? And then based on that, use your formula coming from that. Alrighty, so again, there's this other example here talking about the teacher strikes in public schools in Pennsylvania. And this is the number of strikes they have had over the sample school year. So again, the first step when you're given raw data is starting out by finding your mean. So, and that would be, your actual mean calculation, not any of the other averages. So find your mean. And then remember, we calculate our deviation after that, which is from each data value, then you subtract your mean. And do not worry about getting negative signs. So don't switch that order of the numbers. Don't make it 8.5 minus 7. It's always going to be the data value first minus the mean. So if you get negatives, that's fine. And remember how we were talking about, if you just add the deviations, you get 0 as your total. So to avoid that, you always take these deviation values that you have and you square them. Once you square those deviations, add all of those together, and then that's where we divide by n or n minus 1, depending on if it's population or sample size. That calculation gives you your variation, and then on your variation, if you just take a square root, you get your standard deviation. So how about we pick an example? Okay, so we will actually look at example 6 on page 143 of your textbook. And this example is actually talking more in terms of kind of doing a little bit of a comparison here. Okay, so they're telling us this 3 sets of data have the same mean and range, but they want to know if they will have the same variation, and then what would our answer be if we did standard deviation. So even though they're telling us it has the same mean and range, we still have to figure out what that mean is, right? So let's start by doing that. Let's calculate the mean. And since they're already telling us it's going to be the same mean and range, just take one of those sets and calculate the mean for it, and we'll know it's going to be the same for the rest of them. So do we have the mean? $11? You said what? 9.6. Which set did you use? You used A. What about you? You used C. Okay. Which set did you use? C, and you got 11. Okay. So yeah, it sounds like 11 seems to be our answer here. Okay. You think you left out a number or something like that? Okay. Okay. Let me wait for my OneNote to come up. I don't know why it's taking its sweet time. He does not want to cooperate. So our given data sets okay, so for part A, we had 5, 7, 9, 11, 13, 15, 17. For B, you were given 5, 6, 7, 11, 15, 16, 17, and C, you had 5, 5, 5, 11, and then 17. So for the mean, you should be getting 77 divided by 7, no matter which data set you use, okay? Now, to calculate our variance, let's start with set A here. So the first, and I guess I'm going to do this more like a column. So I'm going to create a column for deviation. The next one I'm going to do as deviation squared. Okay. So the way you calculate deviation is you take your data value and subtract the mean from it, right? Okay, so the set A, my first data value is 5. So that would be 5 minus 11. I have 7, 9, 11, 13, 15, and 17. From each of these, you are subtracting the mean, which is 11. So what will all those deviation values come out to be? -6. Sorry? 7 minus 11? -4. 9 minus 11? -2. Well, that one should be hard. 11 minus 11. Okay, 13 minus 11. +2, good. 15 minus 11. 4, and the last one, 17 minus 11. 6. So of course, this is the part where if we just added the deviation column, we'll get a total of 0, right? Because you can see we've got positives and negatives of the same numbers. So if you add this, you will get a total of 0. So we wouldn't really be able to do anything else. So that's the reason why we usually take our values from our deviation column and we square them. So we will be taking -6 squared, -4 squared, -2 squared, 0 squared, and then of course 2 squared, 4 squared, and 6 squared. So what will those square numbers be? Okay, which will be the same for +6 also, -4, 16, 4. Okay, so let's add up that column now, because that's the total we need. $112. Okay, I just need one more person to verify that total for me, please. Okay, awesome. Would you like to come in? I would like to introduce you to our students, though. So this is Dr. Leah Bornstein. She is the president of Ames Community College.
Hello, nice to meet you. I really didn't mean to interrupt your class. I tried to work from the different campuses at least once a semester.
Oh, wonderful. Well, we are very happy to have you here.
We're happy to have you.
Yeah. And he pays attention. You guys.
Calculate to the seat. Thank you.
Thank you so much. Yeah.
Thanks for
All right, so what's our next step now? We are obviously treating this as a sample. So what would we go from here? Or where would we go from here? Before we get to deviation, we're still working through the variance part, right? Yeah, remember again, as I said, since we are treating this as a sample, you need to divide by n minus 1 and not n. So what's n right now as our raw data? 7. So n minus 1, of course, would be 6. So this is our variance calculation. So that's taking the total. Again, remember, this is your summation. So that's for the total of the deviation squared column. And then you're dividing this by n minus 1. So that's your total of 112. N was 7, so n minus 1, 6, right? And what does that give us? We're not at square root yet. Yeah. Okay. 14. So where did you get 14 from? Are you using set A or are you at a different set at this point? Okay. So I guess we cannot trust Joseph anymore for calculations. So 18.7? Yeah, all righty. I guess we can trust Michael. He has not given us a wrong answer yet. Now, was this the actual answer you got, or did you get like decimals? Oh, 6 repeating? Okay. So let's keep that 6 for now. And then you're approximating it to 18.7. Now, this is the reason I ask you is remember when I was telling you when we are calculating standard deviation, we do not want to use the rounded answer, right? For variance, if they're just asking you for variance, 18.7 is okay. But when you are calculating the standard deviation, which would be taking the square root on variance, which of course is taking the square root of 18 point, that repeating 66666. So all you have to do now is, you should have that 18 point repeating 6 on your calculator, right? You just take the square root of that number. And what does that come out to be? Alrighty. Right, so again, you're going to get repeating, or not repeating, but decimals after that. So rounding it by using our rounding rule to one decimal place will be at 4.3. Any questions on the process of this? What are you not getting?
My calculator.
Oh, your calculator. Does everybody know how to use their calculator? Because I know each calculator has a different step involved on how to do this. Valerie, were you able to get your square root or not? No? Okay, let's take a look at what your calculator does. Let me. So let's do this one more time, and this time we're going to do it with set B. So go ahead, write those numbers down if you don't have it written down. 5, 6, 7, 11, 15, 16, 17. Okay. 5, 6, 7, 11, 15, 16, 17.
So like in the same graph, not graph.
Same calculations, yeah, make a same table.
Table, thank you.
Yeah. Okay, so these guys are 5, 6, 7, 11, 15, 16, 17. So we'll start with deviation. Now again, what is the mean for our set? 11. So take your data value, subtract the mean from it. Okay, if you have those values, can you tell me what those deviations are going to be?
-6 for the first one.
Okay.
-5 for the second one.
Good. -4.
0.
Mm-hmm. 4. 5. 6. Very good. And again, if you add that, that will come out to be 0 again. Now we're going to square each one of these deviations. So that's -6 squared, -5 squared, 4 squared, and then doing the same thing with the positive numbers. And what will this total come out to be? $154. And again, what's our n-1 value going to be? 6. Alrighty, so what is 154 divided by 6? Okay. So to 1 decimal place, that would become 25.7. But if you're calculating the standard deviation, then again, use the repeating decimals. So what does that come out to be? 5.066, and then 1 decimal place, what will that become? 5.1. Okay, so let's see. For set A, we had 18.7 for our variance, 4.3 for the standard deviation. For set D, we've got 25.7 for variance and 5.1 for set B. So just looking at these two data sets, and we'll come back and do C, which one would you say is more varied, more dispersed? B, yeah, because those values are larger, right? The smaller the value is, the closer you are to the mean. So the larger that value is, that means the farther away you are from the mean, which means you are more spread out, or the data set is more spread out. So now we have to see where does set C stand, right? And the set C was the one where you had those repetitions, 5, 5, 5, 11, and then 17, 17, 17. So let's take a look at what happens when we try to calculate variance and standard deviation for this set. And again, what mean are we using here? 11, very good. Since you have a lot of repeating calculations, this should go a lot faster. So what's 5 minus 11? And 17 minus 11. Okay, so that would be 6 and positive 6 squared would be 36. What does that add up to? Again, 216 divided by 6 and minus 1, very good. This should not be too challenging. What do you end up getting? 36. Square root of 36. So what can we say about this data set compared to the other two? Does he have the largest variance and standard deviation? Yeah, it does, doesn't it? Because you're at 36 and 6. For set B, that was 25.7 and 5.1. And set A, 18.7 and 4.3, right? So set A has the smallest variance and standard deviation. So that tells you that data set is the least varied. And let's go back and look at that sets again. In this case, you can see, I mean, we have this cluster of numbers right here at 555, right? Which are all 6 units away from our mean, and we know our mean is 11 for all 3 data sets, right? So, I mean, that happens to be one of the data values also. And then this set here, 17s, are 6 units away from the mean. So even though they are evenly spread out, they are 6 units away from the mean. Now, these guys here were a little bit closer because you have these 15 and the 7s, which is a little bit more closer to the mean, right? Only 4 units away as opposed to 6. And then this one is even a little bit more of a tight structure because now you've got your 11 and 9 and 13 in there, which is also bringing it a little bit closer to the mean. So you can kind of see how that data is spread out, but it kind of helps you see, what that mean along with this calculation of standard deviation. Now we didn't talk about the range, but what is the range for this data set for all of them, because they all have the same data values for highest and lowest? Yeah, because you're going to do 17 minus 5, right? Highest value minus the lowest value. So all of them have the same range. So if I look at the mean, where all of them have a mean of 11 and all of them have a range of 12, so that really doesn't tell us anything else for the set. So that's where this idea of variance and standard deviation comes into play, because, the closer you are to the mean, as I said, the more tight that data set is, the more consistent that data set is. And we were kind of looking at that with our little paint boxes, right? So the more consistency you get, that means the closer you are going to be to the mean. The more spread out you are, then the chances of, those, I think they're talking about how long does the paint last before it starts fading away is going to be more with brand A as it compared with brand B. Okay, so this was actually using the longer method of calculating your variance and standard deviation, where you are having to first subtract the mean, square the deviation, add it together, then divide by n or n minus 1, and then take your square root. But we actually prefer using the shortcut method. So even though I wanted you to see how the longer method works, and that's why we used example 6, because it's a relatively simple example to use. For all our calculations going forward, we are going to be using the shortcut method, okay? So save yourself time, because the longer method does take a lot of time to do that, because you have to do each step individually. We're going to use the shortcut method here. So you can see the formula looks a lot similar to the formula that we just used, but there are obviously going to be some differences because we're doing a lot of that calculation together. So you're actually multiplying your n, the data size n, with summation of x squared. So that actually means take each of your data values and square them, and then add them together. So the symbol means first do the square, then add your total. Minus, this is summation of x. So this is actually adding the data values, get the total, and then square it. So there's two different ways you're calculating. Individually, square the x values and add it together. Add all the x values together and then square it. Okay? And then you're dividing it by n, multiplied by n minus 1. So they're actually using simple algebra to combine the longer formula into this shortcut method. And then like is in the description explaining the two different symbols to you here. So this is the same that teacher strike example we looked at above, but in this case, the first thing that you should be noticing is we don't have to calculate the mean, because there is no subtracting by the mean in this case, right? I mean, look at that formula, there is no x bar in that formula. So you don't have to calculate the mean, but you almost calculate the mean because you're having to add the total of your data values, right? So this part is coming from your mean, because mean, we would have added all those data values together, let's just divide it by n. So that's the only part that doesn't happen, but you still have to do that. Now this is where we're taking each data value, squaring it individually, and then adding them together. So that will become part of your numerator. So those are your totals for 99 and 51 coming from here. Your sample size is 6. So you multiply the first part with 6 times 499, and then 6 times 6 minus 1, or 6 times 5 on the bottom. And you're going to get 13.1 as your variance. Square root of that is 3.6. So 13.1 and 3.6, and you should be able to verify that when you do this the longer way. you're still going to get the same exact result, but your calculation really goes down drastically when you're using the shortcut method because you don't have to do all those elongated calculations. So what I'd like to do is just take one of these sets and use the shortcut method to calculate our variance and standard deviation. So I'm actually just going to use set A in this case. Okay, so using the shortcut method, again, your set A has numbers 5, 7, 9, 11, 13, 15, and 17. Okay, so for the first part, you're just adding your data values. So summation of x, we take 5 plus 7 plus 9 plus 11 plus 13 plus 15 plus 17. Those of you who did the mean using set A, you should actually already have that total with you. 77? Okay. Your next step is taking each data value and squaring it, and then adding. This is the part. Be careful, especially if you're trying to do this all at one time in your calculator. One mistype and you'll have to start over again. You just be very, very careful. This is what I normally do. The way I've written it down is the way I type it in my calculator. So I'll do 5 squared plus 7 squared, plus 9 squared, plus 11 squared, plus 13 squared, plus 15 squared, and then plus 17 squared. Just be careful, like I said, when you're typing it in. When you have that total, let me know what it is. Can I trust you? Don't say that. Go ahead, tell me. No, you're missing 959, yeah. Sorry, Joseph. All righty. So let's see. Let's bring that formula up. So this is what we've done, is we've calculated the summation of x, and we have the summation of x squared, okay? But we still need to do this square part here. We haven't done that. So our next step, whoa. Is going to be, and that's n times summation of x squared, which is the second part, the 959, minus, then you have summation of x squared, which means we'll need to do the 77 squared on that part. And then on the bottom, you have n times n minus 1. Okay, so your n is what for our set here? 7, very good. The summation of x squared is that total of 959 minus the summation of x with the square on the outside is the 77, and then we'll need to square that number. And then you are doing on the bottom 7 times 7 minus 1. Okay, so what is 959 times 7? Alrighty. And what is 77 squared? And then of course 7 minus 1 would be 6, so you do 7 times 6 on the denominator. Okay, so 6,713 minus 5,929. That subtraction will come out to be and then what are you dividing that by? 33. Alrighty, and that will come out to be. You like it? Oh, I'm sorry. I forget about it. I don't need to know this anyways. All right, so obviously standard deviation would be square root of the 18.66666. You should be able to verify those numbers with the first method, right? Let me see if we're going to get that. So 18.7, 4.3 from the first method, and 18.7 here, and 4.3 from the second. But yeah, I mean, it does go faster. And you know, this was just a set of 7 data values. Think about when your raw data could be like we were looking at the frequency distribution examples where you can have 40 states, right? Of data from 40 different states, or I think we have done like salaries of top CEOs and stuff like that. So I mean, you can have data values going anywhere from like 20 data items to 40 data items or more. So the longer method will obviously go a lot longer the more data values you have. So this method definitely goes a lot quicker, but you know, obviously be careful when you're typing the numbers into your calculator because one little tiny mistake and you have to start over again. So just find, you know, what works the best for you and go about doing it that way. Alrighty. So this was just for ungrouped data. Now, if you were trying to calculate again your variance and standard deviation for grouped data, it would be very similar to what you were doing, you know, with the mean calculation and stuff like that, where you would actually need to find your midpoint when you're looking at the grouped data because you only have just your raw data to look at. So in this case, what happens is we are actually still using the shortcut method for the group data also. So you are going to take the midpoint for each class multiplied by the frequency, right? So the way these calculations again are going to work, you're going to take the midpoint, square that midpoint, multiply by the frequency, and then add them up for all the classes. This calculation here is where you're just taking the midpoint, multiplying it with the frequency, adding them all together, and then taking the grand total of that. And then still, if you're looking at sample size, you would divide by n times n minus 1. And then, of course, in that same way, you have this multiplying by n in the front. So if you compare it to this formula that you just looked at, it's going to be very similar. You still have your n minus 1 and n on the bottom and here, but now these guys are being replaced by the midpoint instead of the x. It will be the x sub m multiplied by the frequency here. So very much similar to the ungrouped value, but now you're using midpoint and the frequency for each data. So I think we have an example down here, and then we should have time to do an example of our own. So this one is talking about how many miles 20 runners are running during 1 week. So you can see our classes are going from 5.5 to 10.5, 10.5 to 15.5. So they're only telling us class, but what is this? Limits or boundaries? Boundaries because of that overlap, right? With your limits, I mean the numbers here. So we know those are going to be boundaries. So of course, finding the midpoint is again taking the total of those two numbers divided by 2, and then you multiply by the frequency. So this is where we have two different calculations. One of them is just taking the midpoint multiplying by the frequency to get this column here. So we'll add this column and then at the end take a square on that. But then this other column is where you first take the square of your midpoint and then multiply by the frequency. And as you will notice, those numbers come out to be very, very different from each other because this one here is taking the square of these numbers and then multiplying by frequency. So those totals are going to be very different. But here's the thing. This number here, the number we end up squaring this in our calculation. So that's what makes this guy grow and match up to this number here. So you will notice we're taking that 13,210, which is the total of our square column, multiply that by n, ends up becoming 266,000 something. When you take the square of 490, it also ends up going to 240,000. And that's one thing I'll ask you guys to kind of be mindful of when you're doing this for your homework or on the exam. If these two numbers here come out to be too far apart, so you're getting a 6-digit here, but maybe just a 5-digit here, you did something wrong. Because they have to be very close to each other. I mean, they don't have to be like within a couple numbers of each other, but I have never seen where you have a 6-figure here and a 5-figure here. So that's usually a good way to know, because that's usually where something, when you were doing these calculations, where something went wrong. So these guys should be relatively close to each other, and then divide by your n times n minus 1, and you get your standard deviation. Same thing, take square root of that, and you get your your variance, and then square root of that gives you your standard deviation here. So as you can see, for this example, we're coming up with a variance of 68.7 and a standard deviation of approximately 8.3. But again, that just tells us basically what the spread of the data is. Now, if you were comparing two different samples, it would probably make more sense to see which group performs better than the other. Right now, this is just for one single set of data values that we are seeing the standard deviation. So let's try and do an example with group frequency here. And how about we look at number 26 from your textbook. Okay. So here we're talking about team batting averages for Major League Baseball in 2015. They wanted to find the variance and standard deviation and then compare the results. So you've got your National League here and the American League data values here. So this here is of course your class limits, right? Because you will notice there are no overlaps in your class limits. And then this number here in the middle is your frequency. I kind of just spread it out a little bit just that the numbers are all inside each other. But for this class limit, 3 is your frequency. For the next one, it's 6, 1, and then 11, and 1. So go ahead, get that table down on your, unless you have access to your textbook, but if not, go ahead and write that table down so then we can look at calculations for this. And it will make sense to do these as two separate tables. So start by creating your National League column for your class limit. You've got your frequency. The next one should be your midpoint, and then leave space for 2 more columns after that. And then underneath that, do the American League column. So again, start with your class limits, frequencies, midpoint, and then 2 more columns. So something to this effect. The National League with class limits, frequency, midpoints, and then you need 2 more after that. And then underneath that, do the same thing for American. And once you're done writing that down, go ahead and calculate your midpoint. Do you have all of that written down? All right, if you're done writing it down, your next column should be midpoint, so start calculating your midpoint for each of the class members. Okay, do you guys have your midpoints for the National League? Okay. Is that right? Yeah? Yes. All right. Okay, now the next part is going to be where we're multiplying the midpoint with the frequency. So you're basically taking 3 times 0.244. And then obviously doing that for all of them. So whatever that total comes out to be. If you have the total of that column, let me know. And what are you going to do for that last column where we have to take the square of the midpoint and then multiply with the frequency? How would you set that up? Yeah, so you kind of have to figure out how you are comfortable doing that. Do you want to create a second column, which would be for squaring the midpoint and then multiplying? If you want to do it all in one shot, you can do that also. The only thing I'm concerned about is be careful when you're doing your calculations. Don't mistype anything or any of that sort. So what I normally would do is I would take, let's say the midpoint is 0.244. So I would type that into my calculator, do a square, and then multiplied by the frequency. So basically I have 0.244 squared times 3 multiplied with the frequency, and I am getting a value of 0.178608. Do not round any of these answers, because if you start rounding here, your final answers are going to be incorrect. As terrible as those decimals might come out to be, keep them, okay? All right, so my next one would be 249 squared times 6. So no, those two columns would be different because the F times XM column was only taking 0.244 multiplying with 3, right? For the last column where you have a square on the XM, that's where you're taking 0.244 and taking a square on that first, which means you're multiplying it by itself, right? So you're doing 0.244 to the second power and then multiply by 3. No, no. Yes. 0.178608. What did you guys say? No. Oh, yeah. With this column, we're done with. Okay. We're not coming back to this till we get to the calculation. We're looking for XM column. No, that's what happened. Okay. So 0.244 to the second column. Okay, good. I'm glad you mentioned something because I heard you do that. Yeah. The third one. 2.254. So obviously with the grouped frequency distribution, since we have to, find the midpoint, multiply with the frequency and stuff, this guy does end up taking a little bit longer than we did for the ungrouped, but that's just because the nature of your data here. Some of them, if they are feeling generous, might give you the midpoint already, so you wouldn't have to calculate the midpoint, but you would still have to then find the last two columns and do that calculation. So yeah, these guys can take a little bit longer to get through. So if you are done with this, can you please tell me what our grand totals for both the FXM and FXM squared columns are? All right, wonderful. Warren, do you have a total for that column? 15.21. 15.21. 22 for it. So I just need one verification on that. No? Uh-oh. Sorry, Juan. I think you are about to enter the Joseph category. Okay. Tell me what you got. 2.19. 2.19. And I got a concur from Valerie and Michael. Yeah, because you're looking at a bunch of zeros, right? So it should not go up to 15. Since we don't really have whole numbers in there to bring it up that high. So again, I'm kind of glad you guys are making these mistakes so you know that, hey, when I don't even have whole numbers in there, I should not get a total that high. Because you know what happens sometimes if you have a residual number left over on your screen and you didn't clear it out, then sometimes that can add up. But then the problem again with so many digits is if you mistype your decimal place or do something, yeah, these guys are very, very tricky just in those. So, are you ready to do this for the American League now? No? Okay. You know what? We have 5 minutes left. So let's calculate the variance and standard deviation for the National League, and then we'll come back and do the American League. I mean, who cares about the American League teams anyways, right? All righty. So let me bring back the formula so we can just kind of look at it quickly here. So you'd start out with your n value, and then we're going to multiply it with actually that last column that we just calculated. So the first question is, since this is a group frequency data, what is our n value? And how do we find that n value? Very nice. All right. Joseph, you may be coming back. Now, if you tell me the total, 33, and Valerie seems to agree with that. Yeah? All right, we got 2 more agree. All right, Joseph, welcome back. All righty, so the N value is 33. So this is again for the National League. And variance would be N summation of F times XM squared minus summation of F times XM, this time the square on the outside, N times N minus 1. All right, so we're starting out with 33. All right, now what am I going to put in this first parentheses here? That's correct. Very good. Alrighty. 192038. All right. And that's it, right? This one was already squared with the XM, so we don't have to do anything. Now for the second part, which number are you going to put in here? The F, XM, and then the whole thing squared. The 8.502, very good. But this guy will need to get that square on the outside, right? Adding up the frequency column. Yes. All right, and then, okay, denominator would be 33 minus 1, and then of course multiplied by 33. So again, obviously you're going to get a whole bunch of, what are you doing? Go away. Okay. So that first part we are multiplying 33 with 2.192038. Again, guys, I cannot insist. Be careful when you're typing those numbers in your calculator. And you're taking 8.502 to the second power. What is the subtraction on the numerator? 0.05. He's like already giving a disclaimer. Don't worry, I will not banish you. Not at the end of class. Well, Juan's kind of in there with him. Yeah, okay, so you are actually on the right path. Good job, Alicio. All right, and then you're dividing it by pretty large number compared to the numerator. Go on. Denominator. Okay. Oh, let me get some space here. There we go. Yeah, I mean, obviously you're doing 33 times 32, right? So, all righty. So now it's just a matter of, let me get back to my calculation here. 0.05325 divided by 1056. It is a whole lot of zeros. 1, 2, 3, 4. Okay, so it looks like you don't have a rounding rule. I will have to look for it. I know there should be one. But the idea is when you actually end up with so many zeros in the initial part of your number, you actually round it to the first non-zero. We can't really ignore all those zeros. So this is your variance. So what do you think the standard deviation is going to look like? I know. So just as a rounded answer, will be this guy, but for standard deviation, we're going to keep what you have on your calculator. What does he come out to be? Yeah. About 0.007. Now the idea is that they do better than the American League or not, right? What league are the Rockies? See, I told you we didn't need to know the American League. Who cares? So there you go. All right, guys, we'll finish this second part of it next time.